Testing on YouTube. Let's see. Is it working? Maybe. Testing. All good. Working well. All right. Twitch is working. YouTube is working. Now we just need one last confirmation here. Let's make sure that the Twitter or X is working. And I think we're good. All right. So let's go ahead and start this stream. All right, welcome to another Hoopo stream. Today we got a interesting paper for you guys. This is a computer vision paper about segmentation called SLiME, which is short for Segment Like Me. And I'm actually going to start it here. So this is the figure. This is a figure that's deeper into the paper, but this is the figure that kind of convinced me to do this paper. Here we see a image of a dog and a segmentation of that dog. So segmentation is when you segment any image into its kind of like component pieces, right? Usually this is done with specific classes or categories. You're segmenting cars, you're segmenting trees or something like that. There's a lot of variations of segmentation. It's been a thing for decades now, so pretty much every type of segmentation you can think of has been done. But this one is unique in a couple different ways, and one of the ways that is very impressive here is that just with one example like this, right, they provided one example of here's the image and then here's the segmentation for that image. This model is able to basically generalize to a bunch of other animals, and it understands the concepts of legs and body and head and tail. It's quite impressive. You know, a lot of times these models will overfit to like textures or specific kind of visual appearances, but here it is very clearly understanding the concept of legs, of heads, of bodies, and this is just extremely impressive to me. So with that little teaser, let's go ahead and come up to the top of the paper. How's it going? No Free Will. How's it going, John? How's it going, Ed? And this is the paper. It's called SLiME, Segment Like Me, for segment and then like and then me. Kind of a weird name, but we'll go there. 6 September 2023, so relatively recent paper. And then also it comes out of, I've never heard of Simon Fraser University. Autodesk is the company that makes a bunch of computer-aided design tools. So AutoCAD. I think they also do some other stuff. Let me see. But basically a lot of generic computer drafting software, I guess. I don't know. But I guess they have a kind of a research group within them, and then this paper comes from that. So here we have an image using just one user annotated image with various granularities as shown in the leftmost column. SLiME can segment different test images in accordance with those same granularities as depicted in the other columns. And here the granularity, they're referring to kind of how many individual things are you segmenting this into. So here they're segmenting the dog into ear, nose, eyes, tongue, feet, tail, and you kind of get this one-shot just generalization ability here. It's all dogs, but the fact that it can still find the same pieces in all these other dogs is quite impressive. Okay, so let's go ahead into this abstract, and then we're going to find out here why this is a little bit special. How's it going, Daniel? How's it going, Christopher? Significant strides have been made using large vision language models. So vision language models here, for example, Stable Diffusion, but pretty much any model that combines the modalities of vision, which is images, and the modality of language, which is text. for a variety of downstream tasks, including image editing, image correspondence, 3D shape generation. These are just other things that people do in the vision language space. Inspired by these advancements, we explored leveraging these extensive vision language models for segmenting images. And this is the key part here, is that a lot of segmentation work has relied on these very large labeled data sets. So one of the previous papers that we read on this stream was this one here, Segment Anything. And this is a paper from Meta AI Research where they basically created a segmentation model, but the segmentation model was trained by looking at a huge data set of over 1 billion masks and images, right? So for every single corresponding image, they had a mask, right? And that's basically what is known as supervised learning. This isn't quite supervised learning or fully supervised learning because they were doing some kind of auto labeling. They have some kind of self-supervision going on. But at the end of the day, the intelligence behind this segment anything model comes from the fact that you have a huge data set of images where some human has traced out the object and said, this is an object, this is an object, this is an object, and so on. So that's kind of like the kernel, the seed from which the segment anything model and pretty much most of the segmentation work that you see comes from these types of labeled data sets. But this paper does not do that. This paper uses Stable Diffusion as if it were, right, a giant data set, which is one way to look at Stable Diffusion. When you look at the actual Stable Diffusion model weights, really what that is a compressed representation of a giant text image data set, right? The data set that Stable Diffusion has been trained on is not a segmentation data set where some human has traced out a little thing around each of the things. It's a data set that says, here's a picture, and then here are the words that correspond to that picture. So that's really impressive and really cool that they were able to do that. And we're going to figure out exactly kind of how they were able to be clever about the different pieces of Stable Diffusion and eventually get to a segmentation model that's able to do this kind of impressive segmentation by concept almost. At any desired granularity, using as few as one annotated example. So you literally just give it one example, and then it'll basically understand what you're doing at a almost semantic high level. It's like, oh, okay, I see what you're doing. You're segmenting out the body and then the legs and then blah blah blah. Okay, I can do that too, and it can do that. SLiMe frames this problem as an optimization task, specifically given a single training image and its segmentation mask. Right, so that's all you need. It's basically one-shots from that. We first extract attention maps, including our novel weighted accumulation self-attention map. So we're going to go into what an attention map is, but basically an attention map is kind of a key piece of a transformer architecture where you have this self-attention, which is basically a way for a bunch of features to look at a bunch of other features and determine how much do I agree with this feature over here versus this feature over here, and so on. And it's obviously a very coarse explanation of what self-attention is, but if you guys have ever seen the famous self-attention, attention is all you need paper, the self-attention is here inside this little brick here, the multi-head attention. You scale that up here. You have this scale dot product attention, and then right in here, inside this scale dot product attention, there's this query and the keys, and they multiply together, and this is how you create that attention map. From the SD prior. So here they're referring to the fact that the prior, or the thing that they're starting with, is this trained Stable Diffusion model. Which again, you should think of it, rather than saying, hey, this is just a pre-trained model, think of it as Stable Diffusion is really a compression of a giant vision language data set. This is exactly what I need to have an alibi to work with Stable Diffusion. Yeah, I think it's a really clever use of Stable Diffusion in order to create a very powerful segmentation model. Using the extracted attention maps, the text embeddings of Stable Diffusion are optimized such that each of them learn about a single segmented region of the image. So here, the text embeddings of Stable Diffusion, what they're referring to is that, let me pull up this image here. So this is a pretty good image I was able to find about kind of a latent diffusion model, which is what Stable Diffusion is. But we're going to go through a bunch of this stuff later as we go through the paper, but the part here that I want you to look at is this conditioning. So when you're performing this denoising, which is what a diffusion model is doing, right? It's kind of like removing this noise. You're conditioning the removing and of that noise with something. It can be anything. It can be a canny edge image or something, whatever you want. Most people obviously do it with text, right? So you can type in text and then you remove the noise and you effectively generate an image that is conditioned on that text. But that text, you can't just feed it as is, right? You have to tokenize it and then feed it into this thing here, this text embedding model, which will turn it into a nice little embedding vector, which you can then use to condition this unit here. So they're going to be using that. These learned embeddings then highlight the segmented region in the attention map, which in turn can be used to derive the segmentation map. And this is kind of the key insight that allowed them to come up with this technique. This enables SLiME to segment any real-world image during inference with the granularity of the segmented region in the training image using just one example. Yeah, they're going to keep referencing this over and over again because that's the coolest part of this entire paper, is that all you need is just one picture. One picture and the corresponding segmentation map for that picture. Leveraging additional training data when available, FewShot improves the performance of SLiME. We carried out a knowledge-rich set of experiments examining various design factors and showed that SLiME outperforms other existing one-shot and FewShot segmentation methods. Very powerful. And this is another kind of interesting thing about this paper is I feel like this changes the mindset, right? I feel like up until now, a lot of people were operating in this mindset of, in order to get to the next level of any task, you're basically going to have to do something like this. You're going to have to create a bigger data set than anybody else has created. You're going to have to make a model that's bigger than anybody else has created, and you're going to have to train it for longer than anybody else has trained it, right? So there's this kind of like scale is king, and therefore the best way to get state-of-the-art, the best way to push research forward is to basically just throw money at the problem, huge data set, huge models, huge amount of training. But this paper kind of shows that there's a different way to look at these things, right? And that maybe you can just use the models that other companies train, right? Make a big company like Facebook or Meta, they train the giant-ass segmentation model, or a company like Stability AI, they train the giant stable diffusion model, and then that stable diffusion model is their data set, is kind of the result, is a compressed form of what they trained on, so then use that, right? And that's not necessarily new. People have been doing this for a long time with CLIP. So, for example, even in this paper, they talk about, for example, CLIP here, which is a contrastively trained language image pre-training. This is an OpenAI model, and there's a huge amount of computer vision papers that basically just take the intelligence that's inside CLIP and then use it to do something clever in a slightly different space. So I think people are realizing that you could basically do the same thing with Stable Diffusion, and I don't know, hopefully this is the beginning of kind of a whole tree of research that kind of uses the condensed intelligence inside something like a Stable Diffusion to get state-of-the-art on a kind of unrelated separate task, such as in this case, one-shot and few-shot segmentation. Yeah, exactly. How's it going, Liu and Czechbaled? Okay. So let's get into this. Segmentation is a multifaceted problem, solutions existing at various levels of granularity. So from the perspective of the end user, a straightforward and effective approach to guide a segmentation method is determining what to segment and at the desired level of detail across a broad set of images by providing one or a few set of examples. Okay. By the way, I totally like this, you know? I like a paper that gives you a big image and then it gives you the abstract, and then page one, it doesn't just give you a bunch of related work and citations and crap. It goes straight into a nice, beautiful image where you can look at all the results. Obviously, these are going to be kind of cherry-picked, but this is impressive, right? Look at this. It understands kind of the concept of the handle of a suitcase, the wheels of a suitcase, the top of a chair, the bottom. Like, this is very impressive generalization from just one labeled example. I don't know, I'm impressed. Okay, what are we going through here? This example-driven instruction would provide users with the ability to intuitively define and refine the target segmentations according to their specific requirements. Yeah, so if all you have to do is provide one example, this becomes very easy. You can think of all kinds of products, all kinds of applications where now you could very easily say, this is the things that I want to segment, and now, boom, I have a segmentation model that'll give me the ability to segment those things. Talking about visual effects, facial, segmenting faces, okay, a bunch of other stuff. Here they're going a little bit into previous work, so they're talking about GANs, generative adversarial networks. And these are quite old at this point. People keep trying to bring back generative adversarial networks, but I feel like right now diffusion models are still king. Trains multiple MLPs, excel in segmentation, segments only one region. SegGPT employs one-shot learning, training color randomized segmentation that includes instance and part-level detail. Okay. This is why I don't like related work sections, because it's just a bunch of old shit that doesn't matter anymore, right? It's like, who cares how people used to do this 5 years ago, because it doesn't matter anymore. We have a new technique that's better. So why spend a bunch of limited compute and the limited capacity of your brain to store implementation details for a method that is no longer relevant? And that's kind of my mental reasoning as to why I kind of try to skim through these related work sections, because they're not useful for learning. They're useful for the purpose of citations and keeping this kind of education industrial complex going, right? So they need citations because citations are how they basically get grants and money, and how social credit gets assigned and careers get accelerated through citations. But in terms of me as an end user, and I just want to learn and I just want to know what people are doing and learn things, these related work sections are basically a bunch of crap. Okay. But now that my rant is over, SLiMe employs a single training image and its associated segmentation map to fine-tune the text embeddings of SD through attention maps. Okay, so this is a nice little summary of what we're going to be doing here. Refined embeddings emphasize segmented regions within the attention maps. So you can already kind of see what they're going to be doing here is that they're going to be looking at the attention maps, specifically the cross-attention between the text embeddings and then the image embeddings, or like the kind of latent representation of the image. And the way that attention maps work, actually I should have probably had a nice picture of an attention map here, but this is not what I want. I want a attention map for a sentence transformer. Attention map, sentence transformer. Yeah, something like this. So this is what an attention map looks like in what you're normally used to, which is a transformer that is being used for text data. And in text data transformers, wow, is this what I want? Yeah, so in text, whenever you're dealing with text data and you have this attention map for text data, you have a sequence such as text. I don't know what this GIF is. It seems like a bunch of trash. But the self-attention map will tell you how much each word in that sentence or token in that sentence kind of relates to other parts of that sentence. So here, Mary tried John to go abroad, right? You can see that the word abroad and the word go, very dark value, means that there's a high attention value there, right? What this transformer is basically telling you here is that the word go and the word abroad are highly correlated, highly related, right? The two vectors that represent the token go and the token abroad are kind of pointing in the same direction. They have a high dot product, right? Versus the word to and the word, I don't know here, abroad, to abroad, those are not related, right? So now think about this attention map, but rather than being text and text, it's going to be text and then basically the what's in the image. So it's going to be image and text. So then you're going to be able to look and say, okay, well, this part of the image kind of correlates highly with this part of the text, and then what other things correlate highly with that part of the text? Okay, then all those parts must also be related. So they're kind of, that's kind of the magic of what they're doing, is they're going to be looking at these attention maps, and then through that attention map, you can basically do a couple little steps of optimization and get to a point where you know every part of the image that's kind of related to the same semantic concept, and then you can take that same semantic concept and say, okay, now I have a different image. In this case, here's a different image of also an owl, but completely different owl, and whatever concept was this beak or this set of stuff here now is also here, right? So that's kind of what they're doing. Christopher, I wonder how fast it is. I do not know how fast it is. Yeah, that could be a negative. It could be the case that for every single image, the optimization process requires like 48 gigabytes of VRAM and 10 hours. So I don't know. If that's true, then maybe this paper sucks. But up until now, it's definitely pretty hype. These embeddings can be used to segment multiple real-world images during inference, mirroring the granularity of the segmented region. Through various quantitative and qualitative experiments, we highlight the efficacy of our approach. Even when reliant on just a handful of examples, proves to be comparable to supervised counterparts demanding extensive training, right? And this is the supervised counterparts demanding extensive training is the segment anything, right? So this is where you're basically training an image encoder. You're feeding in images and masks and then basically pushing in gradients like this. And then over time, you get very good image encoder, very good mask decoder. You can also, in the segment anything model, they have this prompt encoder, which allows you to prompt or encode various different types of prompts. So you can say, you can click somewhere on the image and say, what is this? And it'll kind of like basically segment the things that are related to that point that you just clicked. You can also give it text. So maybe you could say the wheel, right? And it'll segment out the wheel. But this prompt encoder is trained custom for this exact model, and it's trained from this giant data set of 11 million images and 1.1 billion masks, right? So that's kind of what they're shitting on here, where, hey, we didn't need that data set, and we have comparable performance. We surpass Regan by approximately 8% and succeed SegGPT by 7%. So I guess this is what they're going to be comparing to, Regan and then SegGPT. SLiMe also performed SegDDPM in terms of MIOU. Okay, so some other thing that they're going to be comparing to. These accomplishments firmly establish our models as a leading contender in the state-of-the-art landscape. It's a weird way of saying state-of-the-art without saying state-of-the-art. I don't know. Okay, related work. We're just going to skip through this. What is semantic part segmentation? It's basically segmentation. Again, you can basically say you're breaking up an image into parts, and then those parts can have some semantic meaning. So why are they bringing that up? Because here, kind of what you're doing is you're saying you're segmenting this owl, but you're segmenting it into parts that have some semantic meaning. In this case, legs, body, eye, beak, and so on. What else? Few shot semantic part segmentation. Okay, so semantic part segmentation, but now few shot. Few shot means that you only have a few examples, right? You're not necessarily taking a giant pre-trained model and then fine-tuning it for some long amount of time on your own custom data set. Here, you're basically taking your model, which comes from your pre-training process, and even the definitions of what is pre-training, what is fine-tuning, are starting to melt away, right? We're starting to see much more complicated setups where you train different parts at different times. Maybe you have multiple fine-tuning steps, but few shot generally refers to the fact that here there's going to be few examples. You're only given a couple examples, right? A couple examples here, just one example. Here, just one example of the owl, and then you get all of this stuff here. And then diffusion models for semantic part segmentation. Now this is, I guess, the full Monty here, where you're doing semantic part segmentation, but also using specifically a diffusion model. And it appears that the SegDDPM, which is what they were talking about up here, is a segmentation based on diffusion models. Let's see what they did. Had explored effectiveness of unconditional DMs for the semantic part segmentation task. So here they were using unconditional DMs. DMs is a diffusion model. So unconditional diffusion model just does not have that text conditioning, right? So the unconditional diffusion model does not have this part here where you can condition the removal of the noise on something, which is usually text. So it seems like they gave some annotated images, used the features extracted, added a couple different multi-layer perceptrons, and then somehow got something that was okay. But this is a 2021 paper, so it's definitely old at this point. Okay. Furthermore, unlike this method, we employed DMs with weights acquired through training on general data rather than class-specific data. We leverage cross-attention maps instead of relying on internal features of diffusion models, as these maps contain richer semantic information. Yeah, and this is... The reason this entire thing works is because there's a very interesting relationship between human language and visual images, right? The visual modality and the language modality are actually interconnected in an interesting way, right? Because language is really just the result of millions of years of kind of apes talking to each other and trying to like describe what they're seeing, and then you kind of create this representation of our real world in kind of these sounds that we create from our mouth, and then people figured out how to write those sounds. But there's kind of this relationship between language and vision that is very deep and very intricate, and this cross-attention map here, right, where you're basically saying, here's the image information, here's the text information, the language information, and which parts of that agree with which parts of the other thing. There's so much kind of intelligence just crammed into that cross-attention map that it makes a lot of sense to kind of look at that and target it and say, hey, what can we gain from that? And that's what they did in this paper, right, is they were able to say, hey, you can actually use this cross-attention map to get a very nice semantic part segmentation. Our method demonstrates the capability to work effectively with a reduced number of samples, as few as one, whereas they do not mention this ability. Okay. Popular and publicly available example of a conditional diffusion model is stable diffusion, right? So stable diffusion is conditioned. It can be used for generating detailed images, in-painting, out-painting, editing images, guided by text prompts. So these are just a bunch of different ways of using diffusion models, right? In-painting, out-painting, this is where kind of maybe you cut out a little part of the image and then it'll fill it in for you. You can also take the image and then fill out the edges, right? There's all these different kind of cool products and use cases that people have come up with for diffusion models. A large body of work fine-tunes stable diffusion or its cross-attention modules to perform interesting tasks. Okay, so maybe they're not extremely original in using this cross-attention module for the stable diffusion. Here's a bunch of other papers that try to do this. So 2022 paper where they fine-tune the text embeddings to add a new object to its style or its image generation. Another 2022 paper where they use the cross-attention module to impose more control. And then a 2023 paper where they edit an image using the SD's cross-attention. And then another 2023 paper where they use the self and cross-attention modules for object-level shape variation. Okay, so maybe they didn't come up with this idea of really looking deeply into that cross-attention map themselves, and here they kind of do point to a bunch of other previous work where people were able to do other things with that as well. Self-segmentation is a technique for segmenting a generated image in its generation process by clustering the pixels in the self-attention map and labeling the clusters with the cross-attention map. Boom. I think this is kind of basically what they're doing. Importantly, self-segmentation focuses solely on objects mentioned in the input text prompt in addition to the background. Different from self-segmentation, we use cross-attention map to calculate the weighted sum of pixels in the self-attention map to get the segmentation mask of each region. So maybe slightly different, but it's kind of the same idea. This gives our method the freedom to do segmentation at different levels of detail as needed. Although these papers explore the applicability of stable diffusion in different tasks, using it in semantic part segmentation is not fully explored. So they're the first people to really do this, basically use the cross-attention map of stable diffusion specifically for semantic part segmentation. Damn, I don't know if you guys can hear that crying. 1 second, I'm going to close this door. All right, I'm back. Door closed. Okay, so they're going to start here with some background on what a latent diffusion model is, what attention is, and so on. So we're going to kind of go into this. You know, I don't like reading the related work sections, but I always like reading the background sections because these are always a great way to kind of refresh, relearn, and reconfirm that you understand all the different kind of fundamental pieces here. Okay, so a latent diffusion model belongs to the class of generative models that and model the data distribution of an input random variable by efficiently compressing the input random variable into the latent space of an autoencoder and utilizing a diffusion model to characterize this latent space. Okay. A lot of different pieces here. So what is the latent space of an autoencoder? So this is what an autoencoder is here. So an autoencoder consists of two different parts. You have an encoder model, and then you have a decoder model, right? The encoder model will take an image and turn it into this latent representation of that image, right? So you're taking this image, which could be pretty big, right? 512 pixels by 512 pixels, and you're compressing it into this little latent image, which kind of looks like nothing to us, but to the encoder and the decoder, it is the image, right? And the way that these autoencoders are trained, they're usually basically trained in this with this kind of reconstruction loss, where they create this bottleneck, right? This latent representation that they are forced to communicate with. So the encoder and the decoder, they're kind of like two people on in two cells, right? I don't know. I'm trying to think of an analogy here, but there are two prisoners inside two prison cells, and they have a little hole in between their prison cells, and they have to shove a little piece of paper in between that hole in the prison cell and describe to the other guy what they're seeing, and then the other guy has to draw what the other guy described in the piece of paper. And then if you do that enough times, eventually that little they start to develop a language by which they can efficiently communicate a large amount of information in this image, and that language is this little latent representation. So that's kind of what a latent representation is, what an autoencoder is, what an encoder and decoder are in that. And that's what this part of the stuff is here. So why do people use these autoencoders, and why do people use latent diffusion models? So actually, let's go here, because I think they're going to describe the latent diffusion model, and then we'll go back to that image that I was about to show. So the autoencoder is trained on a vast collections of images and comprises of two main components. You have your encoder, E, and your decoder, D. Luckily for us, they use the same exact letters here, E and D. Sometimes they don't. There is no police for the variable names. You could really name these whatever you wanted. You could really name the encoder D and the decoder E. So a lot of times when you read these papers, they'll use different letters, and that's makes it more confusing because it sounds like there's different things, but it's just you can choose whatever you want for these variables, right? So definitely don't get scared if you find another paper and you're like, this is a different variable than the first paper. What's going on? It's just they just chose a different variable name. The encoder produces an image embedding for a given image I. So you have some image I, some three-dimensional three-channel image, such that I equals EI. So here what they're saying is the encoded image, which is this fancy script I, is equal to the image fed through the encoder. The decoder aims to map I, right, which is this little latent, back to the image space, ensuring that this is about the same, right? And this is the loss that these autoencoders are trained on, where if you take the image, encode it, and then decode it, you should get the same image. And then you basically use a reconstruction loss where this I and this I should be the same. And over time, you basically get an encoder and a decoder that have discovered this magic little secret language that they can use to pass a huge amount of information back and forth to each other. The autoencoder can be formulated either as a discrete generative model or a continuous one. So one way to think about here, they're referencing the VQ VAE paper. So how do I describe this? What they're talking about here versus discrete versus continuous is that this language that the encoder and the decoder talk to, you can either say that language is basically continuous, right? It's a number from that can kind of go any intermediate value between 0 and 1, for example, right, is a continuous space, right? 0.01, 0.0111. There's kind of an infinite amount of resolution there. Or it can be discrete, right? A discrete space like this would be something like language. There's a limited amount of tokens you can use, a limited amount of letters. So the language that is used by the encoder to talk to the decoder, it can either be discretized, which is what happens in a vector quantized VAE, VQ VAE, or it can be a continuous space, right? It can be a vector of continuous float values. So you can choose either one of those. Optimize using a KL divergence loss. KL divergence is a metric for the distance between two distributions, and it's used a lot in, for example, reinforcement learning, where you want the distribution of maybe the human actions to match the distribution of the robot actions. But anywhere where you have two distributions and you want them to kind of slowly get closer over time, you use this KL divergence loss. On the other hand, the diffusion model is used to model the distribution of the image embeddings generated by the autoencoder. Yeah, so there's different parts of the diffusion model here. What they're referring to here in terms of the diffusion model is they're referring to this part here. They're referring to the UNet. So there's a lot of different pieces in this in what is a diffusion model. So we use the word diffusion model to generally describe this entire kind of process, but really within that there's a bunch of different models. You have your text encoder model here, you have your decoder, you have your encoder, you have your UNet, which itself is also kind of like similar to this encoder decoder, where there's kind of like this choke point that's created here in the middle. So here they're talking about this part of the diffusion model, this UNet, which is actually the part that removes the noise from the actual image, although it's not actually the image. Right? Okay, going back to here. Isn't normal VAE also discrete? Technically, everything is discrete because even a float 32 is at some point discretized, right? Like, your computers, every single computer that we use now, except for quantum computers, is based on ones and zeros. So even when we call things continuous, they're not actually continuous because there's a limited resolution to a float 32. Right, so even a float 32 is binned at some degree. And I use this all the time to argue. Sometimes you will see people talk about images as being continuous, right? RGB values, oh, they're continuous, but they're really not, right? Every single channel RGB is usually represented as a uint8, which is a data type that only has 256 possible values. So you're bucketing every single possible value to one of 256 different things. So the real answer, Christopher, is that everything is discretized. As if you're dealing with a computer or a classic kind of neural Turing machine kind of computer, which is the computers that we do stuff with now, those are all discretized because we have limited resolution data types. But if we were using a quantum computer, now you could actually have something that is actually continuous. Okay. One of the appealing features of a DM is that it can be readily extended to represent conditional distributions conditioned on text or category. Right, so this is where you're conditioning on a text, and category here might be, if you were doing some kind of classification model, a category would be something like car or cat or dog, right? If you were doing a classification model for cats and dogs, cat is a category and dog is a category. In this study, our focus lies on text-conditioned LDMs, text-conditioned latent diffusion models, where the DM is conditioned on text. In a text-conditioned latent diffusion model, we begin with a natural language prompt denoted as B, so this is the raw prompt. We tokenize it to get P. So tokenizing it, you're just kind of breaking it up into these little chunks that are easier to feed into a transformer model, which really just looks at sequences, right? Those sequences of those little chunks, each of those chunks is called a token, T tokens, and each indexed as pi for I in the range of 0 to t minus 1. Okay, so what they're saying here is that there's going to be t tokens, 0 indexed, right? So 1 indexing, you start from 1 to t, 0 indexing, you go from 0 to t minus 1. Most programming languages, except for MATLAB, I think, are 0 indexed. MATLAB is the only weirdo, is 1 indexed. But, okay, so you have basically this sequence of tokens, and pi represents the ith token in that sequence. The tokenized prompt undergoes transformation through a text encoder. So here's your text encoder, G, theta. Theta is the parameters of that text encoder. So unfortunately for us in this diagram, the text encoder is tau. So here it's tau theta, but in this paper, they're going to call it G theta or script G. I think this might be a letter. I'm just going to call this script G. To yield a corresponding text embedding, P equals script G, or script P equals script G of P and theta, right? So this text encoder, it takes in the raw tokens P, and then it has some model parameters, theta, right? So some weights inside this little text encoder, and it produces this text embedding script P. I generally don't like it when people like overload variables like this, where P means something and then script P means something different. That I feel like that generally just confuses people, but I don't know, we'll give them that. Boo, you want to say hi? Come here, Boo. Come here. Say hi. You've already been fed, so you can't complain, Boo. Discrete float values are not independent from each other, while discrete value embeddings are. I don't know. I don't exactly know what you're trying to say there. No free will, but maybe I'm just too stupid to understand it. Okay, this text embedding subsequently serves as one of the inputs for a diffusion model represented as E, or epsilon here, which also has some theta. Okay, for training a text conditioned LDM, we add time-dependent noise into the embedding of the input image. So time-dependent noise, what are they talking about here? So here's another picture, which I think is great. This is the full diffusion model, but this actually shows you kind of more what's diffusion process, like what is actually happening here. So the way that diffusion models work is that you basically start from noise, or actually, let's go back. The way that they work is that you start from an image and then you add noise to it, right? So during training, you can just add noise, right? And you say, oh, here, let me just add a little noise to this thing. And then when you add noise, that gives you a perfect example of here's the image and then here's the image with some noise, and you know the exact noise that you added, which means that you know the exact noise you would need to remove in order to get the cleaner version of that image. So now you can formulate this as a learning process, and you can train a model to basically learn how to remove the noise. And it's not going to remove it in one shot, right? This isn't like a generative adversarial network where you can generate an image instantly. Diffusion models require multiple time steps of noise removal, right? So here you can see how there's T total 9 time steps, and you're kind of removing more and more noise. And the amount of noise that you add and remove is time dependent. And what they mean by that is that here, when you're at time step capital T, when you're ideally starting from pure noise, you can remove more noise, right? And whenever you're training this diffusion model, you can add more noise here towards this side than you can add towards this side, right? Once you're here, you don't want to remove huge chunks of noise or add huge chunks of noise. You just add a little bit of noise, right? And that's basically what a diffusion model is. Now, here, they're doing it directly on the image, but that's not actually what happens in a latent diffusion model. In a latent diffusion model, you're removing and adding noise from the latent, right? So it's like, back to our analogy of the two prisoners, the encoder and the decoder, sitting in opposite cells, and they're communicating by passing little sheets of paper through a little hole in the wall, right? This little bottleneck. What if there was a guy in between that bottleneck who took out the little sheet of paper and then added noise to it, right? He just scribbled out some of the letters and then passed it back through, right? So that's kind of what it means to add noise to the latent, or the language that is being used by the encoder and the decoder to communicate the contents of the image with each other. No free will. You might be correct, no free will. I don't know. I'm definitely not an expert on everything, and nobody is an expert on everything. So if someone tells you to shut up, you can tell them to shut up, because all humans are, at the end, we're just limited by our little brains, you know? Okay, so you have noise that is time dependent, right? And your latent diffusion model is going to be adding or removing that noise to the latent, which is that language that the encoder and the decoder communicate through. We employed the following objective to optimize the parameters of both script G, which is the text encoder. Well, this is kind of interesting. So they're actually optimizing the text encoder parameters. They're pushing gradients into that. That's a little interesting. I did not think that they were going to do that, but let's see what they're doing. Let's see where they go. And epsilon theta, which is the diffusion model. Let me actually green highlight this. So the UNet in the diffusion model, they're going to represent this as epsilon. So here they also call it epsilon theta. So that's convenient. We have the same variable used for this figure and the paper that we're reading here. The UNet is epsilon theta. Here it's also epsilon theta. You mentioned something about GANs. Are GANs completely superseded by diffusion models nowadays? Question from Fed Kepri. Not necessarily. There was a GAN paper that we read recently where people were able to train GANs that were competitive with diffusion models. And I don't, like the way that the kind of model architecture wars over the years work out, like things go in and out of style, right? And sometimes things come back, right? So there is a non-zero chance that maybe 2 years in the future, someone discovers some variant of a GAN, or they figure out that GANs are much more effective in some way, and then GANs make a comeback. Or maybe GANs basically never make a comeback, and we have diffusion models for now to the rest of time. Or maybe a new type of model architecture comes in that supersedes both GANs and latent diffusion models. So unfortunately, the way that things work in machine learning, you do end up kind of learning a bunch of things that don't matter, right? Like, I kind of bring up the example of, like, I spent all this time reading papers on convnets and now they're dead. Now everybody uses vision transformers. So it's just an unfortunate reality of, like, if you're in this space, if you're in the machine learning space, you're going to end up learning a bunch of shit that doesn't matter 2 years from now. And that's kind of par for the course for software as well. So software is similar in that same way, where stuff changes constantly, right? You think about someone who learned how to program in, like, the 1990s, right? They were programming with different programming languages than we use now, and the programming languages of the future are going to be different from the ones that we use now. So you're kind of, like, constantly changing the substrate that you're trying to learn and implement and use, and that's just kind of a reality. But you shouldn't necessarily get demotivated by that, because once you learn one thing, it's faster to learn the next thing, right? So if you understand diffusion models very well, whenever the next thing comes out, you're probably going to be much quicker to understand it than the person who had never learned about diffusion models before. So convnets are dead? Maybe not. Maybe they come back. I don't know. The human brain is a convnet. So the human brain has kind of like the same convnet design. So they could make a comeback. Okay. The aim of enabling the model to acquire the capability to predict and eliminate the added noise, right? So basically the whole point of this UNet inside a diffusion model is to denoise or remove the noise, right? And the reason it can do that is because whenever you were training this UNet, you added the noise, so you knew exactly the noise that you added. So you said, okay, can you remove the noise from this? And then you know what the noise is, so you can say, okay, here's what you should have removed. So that's how the UNet over time learned to basically remove the noise from a latent, which is weird because as us humans, I can't look at the latent and tell you what that means, right? It's, like I said, it's basically a secret language that the encoder and the decoder have discovered, and then the UNet is removing and adding noise from that latent, which is even more crazy. Okay, so here you have the loss for a latent diffusion model. LDM, loss for latent diffusion model, is the expected value. Here you have I epsilon in N01. So this is basically a normal distribution. So it's basically saying that the noise that you're adding is coming from a normal distribution, or a Gaussian distribution is another name for that, right? So it's Gaussian noise at some time step t, right? And then you have your script I, which we know means the latent image, or here, which is what's coming out of the encoder, right? You're taking your actual image, putting it into the encoder, getting your latent image, and that's what the latent diffusion model is operating in. And the latent diffusion model is trying to minimize. Here you have the parallel bars. That means with the little 2 here, that means the L2 distance, which basically means the squared difference between these. So the squared difference between the actual noise, which you know because you added that noise, you added that Gaussian noise, and then the noise that is coming out of your diffusion model, which is your diffusion model saying, okay, here's what I think the noise is, and then you actually know what the noise is, you take the L2 between those, and then that's your loss. So it's kind of like a reconstruction loss for the noise, if you want to think of it that way. IT is the noisy sample at time step t, right? So kind of like as we were saying before, diffusion model is doing this over a bunch of time steps. It's time dependent. The noise is time dependent. So the time step matters here. Okay, we employ SD for 2 main reasons. SD's cross-attention modules exhibit rich semantic connections between text and image embeddings, right? So because this stable diffusion model has this UNet, and because this UNet, you see the conditioning information here, which is going into this text encoder, and then you can see it going in here. Ignore this switch here, but you can see how it goes into the actual UNet. So whenever the UNet here is figuring out what the noise is, right? It's predicting that noise. It's being conditioned. So all this rich information, all this rich text information is coming into this denoising UNet and going into these cross-attention maps here, right? These cross-attention maps between the latent and then this text information that's coming in here, right? So that attention map, that cross-attention map, has really rich information. It's just like it's filled to the brim with all kinds of signal, right? If you want to think of like stuff as somewhere between signal and noise, like the amount of signal in that cross attention module map is huge, and that's really what they're leveraging here. The SD's autoencoder transforms an input image I. Okay, so I guess here they're redefining the image I. I guess they're giving you the dimensionality of that image. So here you have, it's a 512 by 512 image with 3 channels RGB into a semantically meaningful latent vector I. So this is the latent representation of that image coming from the encoder, and you can see how it's smaller, right? And this is the whole reason why people do latent diffusion models, is because a diffusion model that operates in image space, so much bigger, right? So much bigger space. That unit would have to be so much bigger. It would just take so much more memory, so much more time. We ain't got time for that shit, right? So we basically are going to do it in the latent space, and works even better. This latent vector consists of 4 channels and has both global and local information. And here's kind of where I want to break out, because I think there's something interesting to think about here. And another paper that we read on this channel was called Beyond Surface Statistics, Scene Representations in a Latent Diffusion Model. So you guys can go ahead and dig up that paper if you want, or that stream if you want, but I think the important learning that I got and the important piece of intuition that I learned from this stream and this paper is that the latent diffusion model has more information than you even think it does, right? And in this paper, they went and they showed you that they did some kind of other clever shit. They were basically training an extra probing classifier, but you don't need to worry about that. The TLDR is that this latent diffusion model has internal representations of basically the entire global scene, right? So it's not like the diffusion model doesn't really know what's going on, and then once it kind of sees the shape of the dog, then it's like, oh, okay, this is a dog. All right, let me make this a dog, right? The latent diffusion model knows this is a dog basically here. It already knows kind of what it's going to do here, right? And that's what this paper was showing, is that even at step 1, where you're just one step away from pure noise, it already has an idea of like, there's going to be a car here, this part is going to be in front of this part, this is kind of roughly the mask. So you can see how it's not like you need to wait all the way to the very end of the image for the diffusion model, the UNet, to kind of know what's going on here, right? The UNet already knows what's going on way at the beginning here, way at step 1, 2, and 3, when you and me as humans, I just look at this, I have no idea what that is, right? That just looks like noise to me, right? So I think that's another important piece of intuition to think about here, is that whenever they're saying the latent vector consists of 4 channels, has both global and local information, this part here, this latent, and then the UNet itself that is operating on that latent, it is very comfortable with this latent. It kind of knows what this latent is going to represent. It already has a rough idea of like where things are going to be, what things are going to be central. So I don't know. I just thought that it was useful to bring this up, because to me it kind of just further adds more intuition just about how kind of rich and signal dense the UNet inside a diffusion model is, and that latent inside the diffusion model is, right? There's just so much there that you could kind of grasp. Question from M9. How does it know the rough idea at the start? I don't know. So, I mean, one way to think about it is that this diffusion, or the latent, right, is that language that is being used to communicate. So the encoder and the decoder, right, over their long time in this prison cells where they were kind of right next to each other, they developed this language by which they could communicate all the information in this image. So this latent is, in a sense, a very compressed form of the image, right? And that compression is not just a one-time thing. It's something that works for a huge swath of images. So it's like a very, very good compression of visual information, and then that UNet operates on that very, very good compression of visual information. So the UNet knows that, right? And the UNet itself has this kind of bottleneck as well. So I think the combination of just the encoder decoder knowledge then going into this UNet, which itself has this kind of bottleneck as well. I think that maybe that double bottleneck, I don't know. I'm just kind of like conjecturing here, and nobody really knows, right? At the end of the day, these are just kind of a black box system. You feed it the data, it just kind of works. But if you're interested about kind of maybe more information about that M9, I would look at the this paper here. Does it have something to do with the seed? No, it should be completely separate from the seed, right? There was another paper that we read on the channel where they did actually look at that. They looked at basically they found a bug in Stable Diffusion where this isn't pure noise, and you can actually get a little bit of the information of the image from this. So maybe you're onto something there, M9, where if they used an old implementation of Stable Diffusion where you're not starting from pure noise and you're starting from basically an average of the images, an average of the pixel values for the images, which is I think what that paper that pointed out the bug was referring to. Maybe there's something there, but I think this paper is coming out far enough away from that bug that they found where I don't feel like the random seed should have any effect on that. Okay, what other questions? Lujun, Stable Diffusion uses UNet. Which vision transformers replaced ComNet in it? Yes, so here, the fact that there's Q, K, and V here, this is telling you that this UNet is using transformers here, right? Self-attention maps, multi-attention map, cross-attention maps. If you can have UNets that are ConvNets, right? I think the original UNet was a ConvNet, for sure, because, yeah, this is the original UNet right here. You see, it's just a bunch of convolutions. But here, this diagram, these are attention modules. Okay, attention modules, nice, perfect timing. So the diffusion model in Stable Diffusion employs a UNet structure incorporating ResNet blocks. So ResNet blocks are just connections that go around things. Here's a good example of a connection block, or ResNet. So you see this little arrow here that goes around this multi-head attention block and then comes up back through the top. That is called a residual connection, sometimes also called skip connections. I think the original ResNet paper called it like highways or something like that. But basically, they're a architectural pattern, I guess, or something. I don't know how to describe it, but like an architectural feature that is whenever you take basically a signal from a lower part of a neural net and then bring it up to a higher part of the neural net, kind of skipping some parts of it, right? So that's kind of what a ResNet is. A ResNet is the original network that used that idea of residual connections, and that's this paper here, this 2016 paper. Along with two variants of attention modules. So attention modules are the self-attention and the cross-attention, right? This part here, self-attention, and then cross-attention. And I think I have some nice pictures for that. I think maybe no. This is just the picture for that. So let's get to this before we get to that picture. The self-attention block calculates the attention across the image embeddings, capturing relationship between specific elements and other elements within the same image embedding. Right? So in self-attention, you're looking at one sequence and you're looking at the same sequence. So self-attention, the sequence is kind of paying attention to itself. So you're saying what elements in the sequence correspond to what elements in the same sequence, right? That's the self-attention. You're paying attention to yourself. Cross-attention is whenever you're, the two things in your attention map are different. Whenever you have, and I think in the original attention is all you need paper, it's two different languages. So it's like sentence in language 1 and then sentence in language 2. That's what the cross attention there is, but here it's going to be image and text is the cross attention, and then image and image is the self attention. On the other two hands, cross attention computes the relationship between the latent representations of two different modalities, like text and image. An attention block comprises of three components: queries, keys, and values. These are your three matrices inside an attention module. The attention module is a function that transforms an input query into an output using a key-value pair. Therefore, given a query, key, and value with dimension of d, the output is defined as follows. And this is kind of your standard attention equation. If you guys are interviewing for machine learning positions, I feel like there's no way they don't ask you to write down this equation. So this is a useful one to know. But you have your queries, you have your keys, and you have, let me Control Z here, and you have your values. And here's a nice little example showing you what that operation really looks like once you have tensors. But here you have x. X is going to be your actual sequence, your sequence as in your sentence or your image. You have your weights, so similar to how in a multi-layer perceptron you have the weights which represent the actual weights of the neurons. Here in an attention module, instead you have these matrices which are called WQ, WK, and WV, right? Query, key, value. You're multiplying the queries by x, the keys by x. That's going to give you your query you could think of them as like little vectors, and then here's the actual attention operation here where the queries and the keys. So if there's parts of this query, right, if this little row here and this little column here and the key, you could think of them as vectors. If those vectors are in high agreement, then the corresponding value, this is terrible because the word value is overloaded here, but the corresponding attention map value there is going to be very high, right? It's going to be kind of like this. It's going to be very dark, very high value, very close to 1, right? And that's what this square root of d is doing, is just normalizing it. And then the softmax turns it between 0 and 1. But very high correlation versus very low I don't want to use correlation because that has also statistical definition as well. Actually, boom, this is even better. So here you go. Here's an attention map. So each one of these little squares represents basically the dot product between one row of the Q here and then one column of the K. And wherever you have high agreement, you're going to end up multiplying that value by the V. So the values, you're basically what this entire softmax QK over square root of D, what all of this is doing is it's basically giving you these weights, right? It's giving you these weights where this weight is going to be very high, it's going to be close to 1, this weight is going to be very low, close to 0. If the weight is very low, what you're effectively saying is ignore this part of the V matrix or V tensor. Pay this part of the V tensor, very important. This part of the V tensor, not important, not important, not important, very important, not important, very important, right? So it's kind of like this. You're saying the relationship between agreement and économique, nothing. Here European and European, very high. Here this is even further confusing because in this case black means 0 and then white means 1, but I don't know. Hopefully I'm kind of waving my cursor around enough that you guys have an intuition about what is going on here with the attention map. And then if this was a cross attention map, right? Let's look at cross attention. See if we can find a nice picture for this. Images. What is going on here? Yeah, so in cross attention, the Q is coming from somewhere else, right? Yeah, so you see here, this is a nice little recolored version of this, but in the self-attention here, the Q, the K, and the V, which are these 3 arrows here, they're all coming from the same here this is called the encoder, but it's basically they're coming from the same path here. Versus in cross attention, the K and the V are coming from this one here, and then the Q is coming from here. So that's basically what cross attention is. Now the Q is coming from somewhere else, right? In this case, the Q is coming from the text. For the self, the query, key, and values are derived from the image, while in the cross, the query is derived from the latent representation of the image, and then the key and values are from the text. Okay, so maybe it's backwards. I gave it to you backwards there. So the key and the value are coming from the text, and then the query is coming from the image, or the latent image. Vectors pointing in the same direction and have similar length. I agree with that. We extract normalized attention map S. So what is the normalized here? The normalized refers to the fact that you're square root of D'ing there and then feeding it through a softmax. Applicable to both the self-attention and cross-attention modules, and note them as SSA. So SSA is attention map for self-attention, and the dimensionality of that is h prime times w prime times h prime times w prime. Note that this is a tensor, right? It's not three-dimensional, it's four-dimensional now. And then you have SCA, which is the attention map for cross-attention, SCA, cross-attention, respectively. And note how here you have this T, because that T is the length of the tokens. So you see, if you remember, the text encoder has T tokens, or the text sequence has a total amount of tokens T. In this context, H and W represent the height and width of the image embedding employed in the self-attention and cross-attention modules. Okay. In the self-attention module, each pixel P with its input, I don't like the use of the word pixel P here because pixel usually refers to the pixel in image space, but here it's the pixel of the latent, is associated with an activation map which effectively identifies pixel sharing, a similar semantic concept with P. Right? So here, this is an interesting kind of, an important thing to realize is that in the self-attention map, right, in your attention map like this is a cross-attention map, but here's a self-attention map. The words that are, or the visual, in this case, pixels that are related, they're all going to have high attention scores with each other, right? Every part of, here's actually a better example, every part of this beak is going to have a higher score with another pixel that is also part of that beak than it is with another pixel that is part of the background or part of the eye or part of the stick or something like that, right? All the pixels, all the beak-related pixels are going to have a high attention score with the other beak-related pixels. Right, so I guess that's what they're trying to show here. After passing an image through Stable Diffusion, if we select a pixel within on the beak of the bird and examine its corresponding channel in the self-attention map, we will observe that the nearby relevant pixels on the chosen pixel are highlighted with that attention map. Okay, so that makes a ton of sense, but it's important to realize that, right, where the self-attention map is basically going to tell you how you're going to be able to go there and say what other pixels are related to this pixel. Okay, you guys are answering each other's questions. I love to see it. Furthermore, as we move away, the intensity of this activation map gradually diminishes, and since it means that if we select a pixel on, for instance, a bird's beak and inspect its corresponding activation map, within the self-attention, we will observe that it highlights other pixels on the bird's beak while excluding semantically unrelated pixels. Right, and that's kind of the key observation, is that you don't even need to go to the cross-attention map. Even just within the self-attention map, you will be able to basically get segmentations, and that's kind of what they're showing you here, where you have this picture of this lady here. Feeding that through the image encoder, you're getting your latent representation of that face. You can then say, okay, I guess here they're trying to show something more complicated, but all the pixels that are related to the lips are all going to be kind of high scoring with each other on this self-attention, although here I think they're describing the next step, which is when they're going to be looking at the cross-attention map. Additionally, for the highlighted pixels, the brightness increases. Figure 5 displays an image of a bird along with 6 channels, each of which correspond to a randomly chosen pixel. On the other hand, for each input text token PI, the cross-attention module generates an attention map denoted as SICA. This map effectively spotlights pixels within the image embedding that align with PI's semantic within the model semantic space. And this is kind of the next piece of key insight here, right? Is that, okay, in the self-attention map, you can find out which pixels are semantically related. In the cross-attention map, you can now figure out which pixels are related to which token in the text sequence, right? So now you have a way of kind of saying, okay, this specific token within this sentence that is being fed into the text encoder and then being used to condition the diffusion, what are the pixels in latent image space, but then that you can go back to actual pure image space if you wanted to, which of those pixels are related to that specific semantic token, which is pretty cool. For example, if we instruct our model to generate an image of a bear by inputting the text be a bear, and imagine the attention map associated with the token bear, we will observe heightened emphasis on those pixels that correspond to the bear object and within the generated image. Right? And the reason that this occurs is because Stable Diffusion has been trained with such a massive amount of image and text pairs that it's basically figured out, okay, whenever it says bear, there's always this type of bear object, right? There's this kind of bear texture. There's a specific ordering of the kind of bear eyes and stuff like that. It knows what a bear is at a high level. So it's not like bear in Stable Diffusion, the token for bear, right? That text piece is somehow just mapping to the texture of a bear, or maybe just a specific view of a bear. It's like literally mapping to the semantic concept of a bear. And that's just the magic of the huge amount of data that Stable Diffusion has been trained on. Okay. Unfortunately, we spent about an hour going over diffusion models and attention maps, but now we're going to actually get to what they're doing in this paper, even though we kind of already know. And this is going to be the methods section. Prior research has demonstrated the use of cross-attention maps in detecting coarse objects segmented during the generation process, yet there remains uncertainty regarding the applicability of these approaches for finer-grained detection, especially within real-world images. We introduced SLiME, a method that enables us to perform segmentation at various levels of granularity in both real-world and generated images. So this works in real-world and generated images. Real-world images and generated images, those distributions are starting to kind of converge. So I don't know if that's necessarily an important distinction. During our training phase, we first extract the cross-attention map and the weighted accumulated self-attention map to fine-tune the text embeddings, enabling each text embedding to encapsulate semantic information from individual segmented regions. During the inference phase, we use these optimized embeddings to highlight the segmented part and then obtain the segmentation map. Okay, so it seems like basically they're going to be pushing the optimization process, right? They describe that you only need one image, but we're basically going to take that one image with the corresponding segmentation map, and the optimization process is going to consist of basically changing this text embedding model, which they're calling here the optimized embeddings. We will delve into the details of the text optimization first and then the inference process. Okay, hit me. Optimizing the text embedding. We will explain how we optimize the text embedding to learn about the segmented regions. Given a pair consisting of an image, okay, here's your image, and a segmentation mask, here's your segmentation mask. Your segmentation mask is going to be the same dimensionality as your image. You see H and W are the same, but there's no ×3 here. The dimensionality here is ×1. There's only one channel, and that channel is basically the class. So K classes. Our initial step involves supplying an empty text denoted as B, so they start with an empty text, all right, interesting, yielding P, which is the sequence of tokens. It is important to highlight that the number of tokens P, represented as T, must exceed the K classes. Okay, so that makes sense. None of the examples in this are like all of the examples that they provide here are like probably just a dozen at most different segmentation classes. So here you see, for example, 3 or 4. It's definitely not to the point of something like the segment anything where you have these like incredibly busy images that have like a bajillion different things segmented here, right? So here you have a huge amount of classes or categories versus here in this paper, we're really only talking about a handful. The magnitude of T is often significantly large. For example, SD comprises of 77 tokens, enabling the approach to accommodate up to 76 segmentation classes, right? So you're conditioning the Stable Diffusion on the text encoder. The text encoder has a limited, you could think of it like context, but it's not quite. It's basically, it can only take a sequence of a limited length, and that limited length means that you're going to be limited by the total amount of classes that you're going to want, because they're going to be basically fine-tuning this text encoder. The first token present within the P, let's actually highlight this with blue. So max of 76 segmentation classes, which I feel like is totally fine. Like, I can't think of like a real world scenario where you need more than 76 segmentation classes. First token present signifies the start of text token. Then you have the end of text token, possess special functionality. The tokens are subsequently processed through the text encoder, okay, resulting in a derivation of text and resulting in the derivation of text embeddings. I don't know why they call that derivation. That's a terrible use of that word. The text embeddings come out of that. We're going to call those text embeddings script P. So normal P is the sequence of tokens, and then script P is the embedding that represents that text once it's gone through the text encoder. Pass the input image I to the E to get the image embedding, the latent image. Afterwards, we sample standard Gaussian noise, apply it at time step t to get IT. Finally, we feed P and IT into the UNet to get the denoised image embedding I prime. This is kind of just a review of everything we've been talking about. After passing these data to UNet, we extract the first K tokens corresponding to normalized cross-attention maps, SI, more stuff. So you have your cross-attention maps, SICA, corresponding to that token. Right? So you can have a different cross-attention map for every token. SD has several cross-attention modules located in different layers. So here they're referring to the fact that you have different cross-attention modules. Here in this figure, the text is being given into 4 separate cross-attention modules here, right? And they're at different layers within this UNet. And we show that the normalized cross-attention map at the Lth layer with SCAL, and this should be SICAL, which has this dimensionality. We average over different normalized cross-attention maps extracted from different layers because empirically we have seen that averaging enhances the results. Okay, so this is a little bit weird. This is kind of standard for a machine learning paper where it's like, we're going to do it this way. And you're like, wait, why are you doing it that way? And they're just like, oh, well, because it works well. You know, so sometimes you run into these things, but basically it seems like what they're going to be doing is they're going to be looking at the cross-attention map at different layers, and the cross-attention maps here are going to be different sizes too, which is going to be annoying to deal with, right? Because the UNet is getting smaller and then bigger, right? You see that? There's that bottleneck. So they're going to be averaging the cross-attention maps across the different layers of this UNet. Okay. We resize all the layers to an equal size, okay, which they have to do. Finally, the attention map we use in our loss function is calculated as follows. Okay, so the average attention map for token I CA cross attention is the average, whatever average function they're using. It seems like they're using here bilinear interpolation, which is just a way to resize images. There's different ways to resize images. There's cubic, linear. Linear is the fastest and easiest one. They could have actually used cubic interpolation and gotten it probably a better score, to be honest. But okay, they're resizing that image, averaging them, and now that's how they get basically the cross attention map for that token. Now for each of the tokens, we want to optimize the embedding for that token such that the average attention map for that token highlights the ith class region in the segmentation mask. Note that we don't optimize script P0 and assign it to the background class, because if we change the backgrounds, SD won't operate properly. Okay, so I guess they're kind of hard coding the first token in the sequence to the background. Seems pretty standard. We stack so they already averaged a bunch of cross-attention maps. They resized them, averaged them, and now they're going to stack them for each of the tokens, right? So they have basically an average attention map for each of the tokens, which in this case represent the different classes, right? The different categories. So you'll have one for this green, one for this red, one for this purple, and then one for this kind of lighter blue. And stack them together with M to calculate a cross-entropy loss as follows. Okay, so largely what they're using is a cross-entropy loss, which is the standard kind of classification loss that you use basically for everything in deep learning, right? So you have here cross-entropy, and then you have all these average attention maps for each of the classes, and then you have M. What is M? Did they define that? Together with M? I don't know if they defined M. I can't find it. Let's see if we keep going. Maybe they define it later. Although this loss optimizes PI such that AI-CA highlights the desired area, the sizes can be used are significantly smaller than the input image, and the object edges are vague in them. The resulting segmentation is very inaccurate. Okay, so this is why they have to do this little optimization process, right? It could have been the case that they could just look at these cross-attention maps and get pretty much their results, but it didn't work out that way, right? Sometimes it doesn't work out. You have to basically do a bunch of tricks and see which tricks improve. So you can see how they're starting to accumulate tricks here, right? So they have the trick of resizing. They have the trick of averaging all the attention maps, cross attention maps. And now they have to do the trick of, okay, we actually need to run a little bit of optimization here, push a little bit of gradients in order to finally get a segmentation that is clean enough to publish in a paper. To improve the quality, evaluate the accuracy. In conjunction with the cross-attention, we benefit from the self-attention map, SA. There are 3 underlying reasons for using the self-attention map. First, it has rich information about the semantics of the image, and that for each pixel P in the input of the self-attention module, it has an activation map highlighting those pixels that share the same semantic meaning. Okay, so here's what's going on, is that the cross-attention between the text and the image information is not very clean. That's what they're saying here. The segmentation is kind of inaccurate. But the self-attention map, which is between image and image, is very clean, right? The self-attention map is extremely clean because it's like down to the pixel level. It's like saying, here are the exact pixels that correspond or match or have a high attention score with the other pixels of the beak. So they're leveraging the fact that the cross-attention map has this semantic information, but the self-attention map has the very clean mask. So they're kind of combining their powers together, and that's how they're doing this thing here. Let's keep going. Second, the output size of the self-attention is bigger than the output size of the cross-attention, therefore it provides more accurate segmentations. Okay. I would say it's also more accurate just because it's an attention operation that's happening between two the same image modality, right? Versus the text and image cross attention is probably more sloppy because there's information that you could gain from being a little sloppy, right? If you can think of the image and the text, sometimes maybe if you know that the background is white, then it's easier for you to identify the thing as a polar bear. So if you're trying to have a high attention score between the word polar bear and pixels that are kind of white that represent the bear and then the pixels that are white that represent the background, having a little bit of that background makes it easier to kind of like tie those two things together. So I think that's why, or at least an extra reason why I think that the cross-attention map, which is combining text and images, has a little bit of sloppiness to it. It's because the kind of areas around the pixels are also useful. Okay, shows the edges in more detail. Cross-attention layers, and for the same reason, we use several self-attention layers, averaging them as this. So, okay, so they average the cross-attention layers, they're doing the same thing with the self-attention layers. The reason that we do not have the resize is that the number of channels in the self-attention map depends on the size of the self-attention map. Okay, in order to be able to average them, we should have the same number of channels. Okay, so I guess they don't need to resize them. Now to use the self-attention map, we resize the cross-attention to the size of the self-attention by linear interpolation, call it RICA. Okay, a lot of resizing and a lot of averaging here, and they use linear interpolation, but there's better. There's cubic image resizing. Yeah, let's see. Cubic image resizing, scikit image. Cubic. Bilinear. I think I've tried to find this before, but I couldn't. But TLDR, there's different ways of resizing, and linear interpolation is actually kind of the worst one. I feel like they really should have done the cubic one. By doing this, for each pixel P in RICA, we have a channel ASA that highlights the relevant pixels in P. Then we calculate the weighted sum of channels ASA and name it SIWAS, WAS attention map, which I think they define up here. Yeah, weighted accumulated self-attention map. Okay, let's see. Now we know kind of what they're doing, so we can actually go into this figure and kind of extract some information from it. Okay, so we have our little UNet here. We have ResNet layers, we have self-attention layers, and we have cross-attention layers, right? They're kind of spread out all throughout. You have self-attention and cross-attention throughout this UNet. To extract the WAS attention map of the ith text token with respect to an image, we follow these 3 steps. Okay, you feed the ith tokens embeddings ti together with the embedding of the image to the Stable Diffusion. Okay, so here's your token I, which is the embedding coming from the text encoder, which is being fed the specific token I. That's pi here. And then it, which is the latent image at time step t. Those are going into your UNet. The UNet is basically going to predict the noise, right? That's what the UNet does, predicts the noise, so you can remove it. But they're going to go into this UNet and take out the self-attention maps and the cross-attention maps. They're going to resize them. So your resize and average. And then here, I guess they're going to flatten. What is this flattening? Then calculate average I cross-attention by extracting the cross-attention maps of the ith token from several layers, resizing and averaging. Then extract the self-attention map from several layers and average them, which is what we got. Okay, and then 3, flattened the average cross-attention and calculate a weighted sum of the channels of average self-attention by weights coming from the flattened cross-attention. Okay, so this is the part that we haven't gotten to. Let's go read that part in the paper, but it seems like they're going to flatten the cross-attention map and then use that as weights for the average self-attention map. Right, so actually kind of similar to what's going on in here, right, where you're looking at the queries and keys and then using those as a weight for the values. So kind of in a hand-wavy way, it's kind of similar here, right? You're using this cross-attention as weights to pick the self-attention stuff. Let's go down, though, because we didn't get this flattening operation. Here we go. The weight of each channel is the value of the corresponding pixel in that channel. SI WAS is the sum of the flattened RICA element-wise multiplication by ASA. So ASA is the self-attention. RCA is this linear resized cross-attention. So they resize the cross-attention, flatten it, and then element-wise multiply by the self-attention, sum those all up, and that's what they're calling the WAS attention map. So it's kind of this big hodgepodge of resizes and flattenings, but at the end of the day, all of the information is coming from the self-attention and the cross-attention maps of the UNet inside the latent diffusion model. I guess they resize it even more. Okay, so they take this SI WAS, resize it again, and turn it into QI WAS, and then calculate the mean squared error. Here's a little standard mean squared error. MI is the binary mask. Okay, so finally now we know what MI is. It's a ground truth mask. The ground truth is coming from the fact that you're providing one labeled example, right? That one labeled example has basically, it has the picture that you want, and it has the masks, or the segmentation. Segmentation is a mask, right? You could think of this as basically just being 4 different masks, right? You can imagine a image that looks like this, but it's all black and the only thing that's white is the head. And you can imagine an image that's all black, but the only thing that's white is the body. So any segmentation image is just a bunch of masks. That's another way of representing that same exact thing. So that's what this is. MI, there's going to be I total masks, where basically you have I classes. So that's the loss, MSE loss here, that you're going to be using. You're summing that over all of the K tokens. And then tokens are classes in this case, right? And you can have up to 76 classes because the text encoder in Stable Diffusion takes up to 77 tokens. Okay. Pixels belonging to class are 1 and all the other pixels are 0. Okay, the last loss function that we use is the Stable Diffusion loss function L latent diffusion model, which they described earlier, which is the MSE loss between the added noise and the predicted noise. We use this loss because it prevents the text embeddings from going too far from the space understandable by SD. Okay, so it's kind of like a regularization loss, and ultimately the loss that you're going to be using to optimize the text embeddings is a combination of these 3 different losses here. You're going to have your cross entropy loss between all the different cross attention maps that are averaged for each of the tokens or each of the classes, right? And the mask. So you see here, this is the mask. Then you have a mean squared error loss where you're basically doing the MSE between this weird SI WAS, which is kind of like this weighted average self-attention. So this is kind of where the self-attention map is coming in. It's coming in through this SI WAS, which is coming in through here. So you have the cross-entropy loss, which is largely the cross-attention stuff, cross-attention maps. You have the MSE loss, which is largely the self-attention maps, right? Weighted by the cross-attention a little bit. And then you have this LDM loss here, which is just your standard noise reconstruction, if you want to think of it that way. I know some people might cringe at me calling the MSE loss between added noise and predicted noise a reconstruction loss, but that's kind of what it is, right? You're trying to say this is the real noise, this is what you said the noise was, and what's the difference between those. So kind of a little bit complicated, lots of different pieces here. I don't like all this weird shit that they're doing here with the resizes and averaging. You know, that stuff, a little bit cringy, but, you know, it works super well. So this is the loss. They have 2 hyperparameters here, so they're going to have to figure out the magic value to pick for this alpha and beta hyperparameters here, which is going to basically be a trade-off between how much this loss matters versus this loss, and so on. Okay. Inference. Damn, dude, we're already at hour and a half. How much time do I have? I guess we can probably skip over the experiment. So let's look at the inference part, because this is the question that John keeps asking, is how fast is this? During inference, our objective is to segment the test image at the same level of detail as the training image. To achieve this, we begin with a test image presented as iTest. Okay, so this is your one labeled example, and encode it into the latent space. Following this, standard Gaussian noise is introduced, magnitude determined by the time parameter t. Okay, time-dependent noise. Let's take another sip of yerba mate. It's important to note that this t and the Gaussian noise value remains consistent with the choice and training time. A comprehensive analysis of the selection of the specific t is provided in detail. Subsequently, we employ the optimized text embeddings along with the encoded image to derive corresponding cross-attention maps from the forward pass. These attention maps are shown enable us to obtain this SI WAS for each text embedding. And then the next steps involves selecting the first K WAS attention maps that correspond to the K classes. These selected maps are then resized using bilinear interpolation to match the dimensions of the input image and then stacked along the channel dimension. Damn, so much resizing in this. Subsequently, we proceed to generate a segmentation mask by forming a argmax calculation across the channels. Okay, so once you have basically for each token, you're saying, okay, well, there's K classes. Each of my K classes have their corresponding token. I'm going to say, I'm going to end up with basically a probability of like, what is the probability of this pixel in the image corresponding to K equals 1, K equals 2, K equals 3, K equals 4. You just pick the one that has the highest, which is the argmax, right? You're basically saying which of the K makes the most sense for this pixel, and that will fundamentally give you the new segmentation masks, which is how you can get these, right? So these are predictions coming from this inference process. Important to note that the process can be repeated for multiple test images without requiring any pre-training, any retraining. They don't really give us an idea of how long this takes, though. You know, it would have been nice. Maybe they give it down here. Horse class. Our methods IMIOU against others on a horse class of Pascal part dataset. Okay, so now we're going to go into the part of the paper where they basically just show you how this works, compare it to a bunch of other techniques, and compare it to on a bunch of different types of images, right? There's lots of different types of images, like for example here, Celeb Mask AHQ. This is a data set of like close-up pictures of people's faces, and a lot of times it's less and less so the case because we're dealing with kind of, as the field of machine learning is progressing, the ability to transfer to slightly different types of images is becoming more and more kind of just free You know, it used to be the case that if you did a technique or if you wrote a paper and you only used kind of a SLiME mask type data set, it wouldn't work for something like this, right? Something like animals in a field. And likewise, if you had something that worked for animals in the field, it might not work for SLiME HQ. But we're getting to the point where Stable Diffusion works for pretty much all types of images, so therefore it would make sense that this technique is going to work for a bunch of different types of different image datasets, such as SLiME Mask HQ and then Pascal Part. Shows SLiME superiority by evaluating on 2 datasets, Pascal Part and SLiME Mask HQ. So again, they're kind of explicitly picking 2 datasets that are kind of visually different, right? The dataset distribution of SLiME Mask and Pascal Part, they're not right on top of each other. They're like slightly separate, right? There isn't a huge amount of overlap in those image distributions. Were conducted over 3 times, different initializations, report the mean and standard deviation. Only evaluate on car and horse classes. As the paper we compare with, report the results only for 3 classes. The metric we use for reporting is mean intersection over union. That's what MIOU. You guys would probably know what IOU is here, but intersection over union. I think it's super easy to understand with a picture. Here you go. Area of overlap over area of union is the intersection over union. And then the mean IOU is basically the average of that over an entire test data set. So that's what MIOU is. So a MIOU of 1 is perfect, and a MIOU of 0 is garbage. So you see here, mean IOU. I guess they CNN plus CRF. So supervised learning approach, if you were to use a ConvNets, I don't know what CRF means. I don't know. But honestly doing pretty good. Supervised learning still pretty good, but 10 sample versus 1 sample, that's actually kind of bad. Look at that. If you give it 10 examples versus just 1 example, the difference is actually not insignificant. You're getting 51 versus 34. Ooh, that's not... Ooh, maybe these examples are a little bit cherry-picked. I don't know. Ooh. I would have thought that the 1 sample would have worked just as well than the 10 sample, maybe just a little bit worse, but the fact that it's sometimes significantly worse, that's not good. That's not good, guys. Okay. To maintain fairness, we optimize our method using 10 and 1 annotated images. So they're kind of comparing, do you give it 10 examples versus just 1 example? Subsequently, we present the results obtained, blah, blah, blah. Okay. Focuses on object parsing and semantic part segmentation. Let's actually look at what this Pascal part dataset looks like, right? Let's get an idea of what this looks like. Pascal part looks like this, so it's kind of, there's a nice variety here. You have an outdoor image, you have vertical images, so different image sizes. The segmentations here seems to be like head, body, stuff like that. Let's actually see. Okay, but you know, these are definitely very different from the mask SLiME data set, this one. This is your mask SLiME. Looks like that, right? So definitely different kinds of images, right? Even though they're both humans, it's like a completely different kind of image. These are always face shots, always centered, always square. Versus this here, you kind of have a lot of weirdness going on. We use car, blah, 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 horse. The result, our method, SLiME, outperforms Regan and SegGPT on most of the parts. Good to know. SLiME outperforms Regan on the 10 sample setting. Outperforms SegGPT. SLiME is truly a one-shot technique. I don't know about that. Here they're saying SLiME is truly a one-shot technique where we only need a single sample for training. But this tells me a different story. Here it's telling me that SLiME is, sure, you can use one image, but if you use 10, it works way better. So it's not as one-shot as I thought it was going to be when I picked this paper. Christopher H. Dropping some knowledge on us. Apparently, CRF means conditional random field, CRF. So they're applying that on top of the ConvNet in order to get a baseline for a supervised learning approach here, which actually performs quite well. Okay, let's keep going. So this is the horse class. Now we're going into car class. Ooh, okay, this is a little bit more similar, right? Maybe not. So you can see how the difference between 1 sample and 10 sample is object specific, task specific, and part specific, right? So the body of the car, SLiME can pretty much immediately recognize that with 1 sample. You only need 1 sample to show SLiME that it's the body of a car, and it pretty much gets it. But the light of the car, right, the little headlight, it's a much more difficult concept to kind of pass on to SLiME. So this is kind of where it gets interesting, right? Because fundamentally, the intelligence of SLiME is coming from Stable Diffusion, right? And Stable Diffusion has built this very complicated internal relationship and representation between text and images. So it would make sense that more weird, nuanced kind of like things such as the light in a car, or maybe like here the plate, I don't even know what the plate of a car is, I guess the license plate, those type of things might be harder to kind of semantically get the concept across for SLiME than something like the body of the car or the window of a car or the background. Like the background here is actually really good. But also, this is less impressive than I thought, because this is the techniques, Regan and SegGPT, that I was kind of talking shit on earlier, and like, look at that. They're actually competitive, very competitive. Huh. Okay, so now they do the same thing with Celeb Mask HQ. They're going to be comparing to SegDTP-M. Table 4 shows our quantitative results. As shown, our method outperforms Regan and the 10 and 1 sample setting. 10 sample setting, SLAM outperforms. There's a discrepancy between their performance in several classes. Yeah, it's like class-specific performance. SLiME performs much better in clothes and ears, but did not perform well for the nose. That's kind of a weird one. Regan utilizes StyleGAN, which naturally performs much better than SD on human faces. Ooh, okay. So here you go. It's why is SLiME not performing as well as Regan? Because Regan comes from StyleGAN, which probably had a Celeb HQ dataset in it, versus the Stable Diffusion models, right, which are effectively just a compressed form of the Stable Diffusion dataset. That doesn't have as many human faces, right? So it's just not going to be as good on human faces. It's pretty good. That fits my intuition, you know, and I love it when conclusions fit my intuition. We can segment other objects with no pre-training on their class thanks to the semantic knowledge of SD. Having SD tailored for facial images will help improve such differences but hurt generalizability. I don't know. I think that the bigger, better SD model of the future will just be better in every single way. So, average MIOU of different methods. You have more comparisons here, kind of beating these out, I guess. Suave, MAE, SegDDPG, DDPM. Here's the results on Celeb Mask HQ. Here they're showing you, for example, they said the nose was terrible, so 68 versus 72. What? That's weird. You do better with just one example than you do with 10? What the fuck? Ear, if you give it 10 examples versus one example. This is so weird. Why do you get better results with just one shot than you do with 10 shot? What that tells me is that the one example that they fed it was probably good, and then the 10 that they gave it probably were worse. So there's probably there's probably a couple examples in this 10 sample that are trash, And what's happening is that the one sample is a better... With the one sample, SLiME says, okay, I know this is a nose. But with the 10th sample, it's like, wait, I don't know what that third image is. This is maybe not a nose. And so that kind of confuses it. So I don't know. I would love to see what the 10 sample versus the 1 sample is, because maybe that's kind of why you see this weirdness here where you get worse performance on the 10 sample than the 1 sample. SLiME either outperforms or performs comparably. Ablation study on text prompt. Minimal effect of initial text prompt for SLiME. Part names. MIOU when using all part names separated with a space. So background, body, light, plate, wheel, window, right? So remember that they're feeding the text into the text encoder, and each token in that text sequence is the classes, right? So the K tokens are the K classes. So here, for when they're segmenting the car, they're literally feeding in the words background, body, light, plate, wheel, window, versus, I guess in this case, they're using part, so that it's generic. SLiME with its final settings employing an empty text prompt. Minimal effect of the initial text prompt for SLiME. So I guess it doesn't really matter what you put in there, because ultimately you're running this optimization process to get the best tokens. Yeah, okay, so actually I was actually incorrect. So I think a couple times in this stream I mentioned that they're pushing gradients into the text encoder, but I don't think that's actually what they're doing. I think what they're optimizing is the actual text tokens themselves. So basically the point of the optimization process is to say this part of the image, which according to my self-attention map is related to these other pixels in the image, what is the corresponding text token that corresponds to that, and then let me push that text token in the direction of that. So it's kind of like you're creating a new token which represents the nose. You're creating a new token which represents the face, and so on. Okay. In this section, we showcase the versatility trained on an occluded object and subsequently infer test images without the occlusion. Okay, so here they're occluding this image of the car with this dude, and then they say, okay, I just want the car, and then it's able to basically segment the full car without that line in the middle, which goes to show you that it's understood that what you want is the full car, not just like the left part and the right part of the car, that you're actually interested in the full concept of a car. And it's actually kind of interesting here where it segments out the other car. You see that? So it doesn't just segment the BMW here, it segments out this truck and then this little car in the back as well, because it's like, oh, you want the cars. All right, here's the cars. Similar kind of thing here happening with some bears, where you're providing this single image example here of like, here is the bear, and then he's like, oh, okay, you want the bear? Here you go. Here's the bear. This is also a bear. This is a bear. Look at that. Look at these beautiful little bear boys. Okay. Put to test occluded portions. Method's capability to comprehend part and object semantics, which is basically coming from the fact that you have this rich vision language understanding coming from the Stable Diffusion. The fact that Stable Diffusion is trained on captioned images. Alternatively, illustrating scenarios where a training image depicted as a bear is entirely visible while the test image is subject to occlusion. Okay, now we finally get to this part, which I thought was the coolest part, where it's able to kind of like generalize to other animals. So badass. And then here they're just kind of showing you that it's able to generalize the concept of a dog, right? So it's not like by highlighting this thing, you know, one possible failure case is it could have said, oh, okay, you like gray texture, so let me just highlight other instances of gray texture or other instances of quadruped. No, it's not doing that. It knows that you want a dog specifically. So even when you feed it this example here, and you have a horse, which is kind of like a dog, right? It knows, no, you don't want a horse, you want specifically the dog. So that's kind of the impressive part here, where it's like, it's not just thinking quadruped or mammal or furry texture or like nose and ears, because all of these animals have noses and ears and furry texture and are quadrupeds. It's like very specific about the concept of a dog. That's kind of an easy one, though. I wish they would have done something more difficult, like a zebra and a horse, or like two animals that are more similar than a horse and a dog. Okay. Initially present qualitative comparisons, conduct a comparative analysis using two camouflaged animals, namely a crab and a lizard. What? Where's the crab and the lizard? Here you go. What the fuck? Okay, so they segment out this crab, and it's able to detect the crab. This is kind of a cool example, right? Because I guess these animals, the texture of the animal in the background is almost identical, but look at that, dude. You can't hide from slime. Slime will find you, even if you're wearing full camo. Damn, dude, that's impressive. Damn. Superior performance compared to SegGPT. So this row down here is the SegGPT, which is obviously way worse than the SLiME. Pretty badass. Okay, implementation details. We're almost done here. Perfect timing. We choose SD version 2.1. Okay, so that's definitely post fix, the noise fix that we were talking about, where the noise here at the front was actually incorrect, but I think SD 2.1 is post that fix. We extract the cross and self-attention maps from the 8th to the 12th layers and the last 3 layers of the UNet. Okay, so they're not using the early layers of the UNet, just the last ones. They start with the empty text prompt. We use time step equals 20, where t is in the range of 0 to 1,000. Okay, so we were looking at this paper here, right, and we kind of came to the conclusion that you could have probably actually used the first time step, but they use time step 20 out of 1,000, which means that it's kind of more like maybe this one here, right? Maybe step 2. We avoid higher values as they produce noisier images. Also, at the beginning of every training, we randomly sample Gaussian noise. Then we use the same noise in the inference. We use an atom optimizer with a 0.1 learning rate and batch size with gradient accumulation of 4 epochs. Look at that learning rate, this monstrous learning rate. To calculate any of our loss functions, we resize the ground truth mass and our predictions to the size of 128 by 128. In addition to that, we set alpha and beta equal to 1 and 0.05. So these are the hyperparameters that they were using for the multi-part loss function, which is used to optimize the tokens. For preparing the Pascal part, we follow the procedure of regan, and that because they're not pushing gradients into the text embedding model, right? They're basically what they're optimizing is the actual token value, right? So that's why they have this monster learning rate, because they're optimizing the value of a token, not the weights of a neural net. We start by cropping the object images with a bounding box. Afterwards, we remove those images with our bounding box, have an overlap with more than 5% bounding box. Okay, so this is some bullshit data prep that they do for the Pascal part data set. Some more little details around the data set. Let's get to this conclusion here. We propose SLiME, a one-shot segmentation method capable of segmenting various objects in various granularity. We show its superiority through an extensive set of experiments and comparing it with state-of-the-art and few-shot supervised methods. We showed that although SLiME does not require training on a class or object or a large set of annotated segmentation masks, it can outperform other methods on average and at most, and also most of the part segments. Our method is capable of learning to segment with as few as 1 annotated examples. SLiME may result in noisy segmentations when the target object or part is extremely small. Okay, so it doesn't deal well with small things. We extract from the SD to use it as a segmentation prediction. To counter this, we employ bilinear interpolation. Again, I feel like they should have used the cubic for map upscaling. Due to scaling, certain pixels might be overlooked, leading to the described noisy outcomes. Resolving the mentioned limitations and making the optimization process real-time and applicable to videos would be an interesting future direction. Yeah, so you still have to run this optimization process. Here they say 150 steps. Where is it? Right here? 150 epochs. So, I mean, it's hard to say how long that's going to take. But let's see if they actually give us an exact number. They don't even tell us, like, I want to know the exact... Okay, so this is how they find the correct time step to do it at. So the time step in terms of here, right? So you pick a time step along this diffusion process. They tried a bunch of different ones. They found 20 was the best one. Here are different learning rates. Text embeddings deviate a lot. So they tried different learning rates. Learning rate of 0.1 was the best. What else we got? They don't. John, I feel like they never answer your question. I'm sorry. They never tell us how long this takes. They never tell us what they ran this on. Usually papers do that, right? Usually papers will say, this optimization process took 10 seconds on a 4090 GPU or something like that, but they never say that. So we kind of have to guess. I feel like you could definitely run this on a single GPU. If I had to guess, this is probably like 30 minutes. Maybe an hour max. I don't know. It can't be more than an hour on one GPU, if I had to guess. It's probably way shorter than that. But wish they would have mentioned it. All right. We're almost at the end here. We got 5 minutes. Let me see if I can summarize this paper real quickly, answer some of your questions, and we'll get going. All right. So today we read the paper SLiME. This is a paper coming out of Autodesk Research, which does a bunch of computer-aided drafting, kind of like engineering tools. I guess they have a research group, and Simon Fraser University. This comes in 6 September 2023, so really recent paper. And what this paper does is it basically uses Stable Diffusion as a prior for a one-shot semantic part segmentation model, right? And we're used to segmentation models such as this one. This is the Segment Anything coming out of Facebook, which learns the process of segmentation from a absolutely monstrous data set of 11 million diverse high-resolution images and 1.1 billion masks. And this is a good example of kind of what a supervised learning process is, right? Where you have image, mask, image, mask, image, mask, and you just keep pumping your model with that, and then over time it gets really good at given image, what's the mask. Segment Anything is a little bit more complicated. It does its own labeling. It kind of has this kind of like self-supervision little magic in there, but it is kind of at the end of the day just supervised learning to the mask and image pairs. This paper does something different where it's using Stable Diffusion, and it's leveraging the fact that Stable Diffusion has a very, very interesting cross-attention map, right? The cross-attention map inside the denoising unit of Stable Diffusion has learned this kind of attention mechanism between the tokens of text coming, or these text embeddings, which are text information from the world, and this latent image here, which is really image information from the world. And it's learned a way to kind of like determine which parts of that text are relevant to which parts of the image, such that it can remove noise and then generate images for you, which is what Stable Diffusion is used for. But in this case, in this SLiME paper, they're using it to basically say, okay, well, what I have some tokens here, or some parts of the image, other parts of the image that are related to this part of the image from the self-attention map, and then what token corresponds to this part of the image, right? And then they run this optimization process where they basically figure out what token represents this part that you gave it. So all you're giving to this SLiME model is a picture and then the segmentation that you want. So you're giving it one segmentation map, which is a series of binary masks, if you want to think of it that way. And SLiME is going to figure out, okay, this is, over the course of some optimization that it does, it's going to say this is legs, this is head, this is tail, except it's not actually going all the way to saying head or tail or legs. It's creating a new token which kind of represents that concept. So maybe the concept of horse head is slightly different than the concept of penguin head, right? So very cool application of Stable Diffusion. And to me, this rhymes a lot with a lot of the computer vision literature that uses CLIP in a similar way, right? Where you're using this giant pre-trained CLIP model to do something fancy in a different task. And here they're doing the same thing where they're using this giant pre-trained Stable Diffusion model to do something fancy in the segmentation world. What else? Very nice little summary of latent diffusion models, of attention modules. I guess we never went over these figures, but basically what they're doing is they're taking the cross-attention and the self-attention maps, and they're doing all this kind of weird like resizing, averaging, just because the size of these maps is going to change as you go across the UNet, and they're going to use a bunch of them over the different layers of the UNet. So they have to do all this like averaging and resizing, which is a little bit weird. I don't like that, but the results kind of speak for themselves. You know, these results are quite impressive. The quantitative results are actually kind of trash, right? Because it doesn't seem to perform that well, but then the qualitative results are very impressive. So this result here, impressive. The bears are impressive, and this is, I think, the coolest one. But yeah, that's pretty much it, guys. We got a minute left here. Very cool little segmentation paper. Hope you guys learned something about diffusion models, learned something about segmentation models, and how you can use those. And I hope that this inspired people to kind of do something cool with Stable Diffusion, because I feel like there's so much more awesome shit that people could be doing, and you could be one of those people doing that. Are they releasing the code? I have no idea. I'm about to get cut off, so I'm going to end it there. Thanks, everybody. Thanks, M9, Chris, John, No Free Will, who else? Fed Kepi, Random Thoughts, Lu June, Khalil, Ed. Everybody, thank you for watching, and see everybody later.